Okay, so let's look at sections 18.1, 18.2, and 18.3 from Newton. And this is all about exponential functions. So first I want to refresh your memory on the laws of exponents, because we'll need them later. So here are the laws of exponents that we need. If I have a to the power of s times a to the power of t, this is when I add the exponents. If I have a to the s to the t, that's called powers to powers. That's when I multiply the exponents. Then I have the product to powers, so that's a to the s times b to the s. And just a reminder that if you have something like 2x to the 5th cubed, that the 2 has to be cubed and the x to the 5th has to be cubed. That's what this property is referring to. So then 1 to the s is going to be 1 no matter what the exponent is. A to the negative s is 1 over a to the s. The best way I think to think about negative exponents is as reciprocals. And then a to the 0 is 1 as long as a is not 0. In calculus, you will run into 0 to the 0 and learn a lot more about it. So now I want to make sure you can do exponentials on your calculator. So I want you to do some examples and check with me to make sure you get the right result. And we're going to round to 3 decimal places. So for A, I get about 8.815. And as soon as I round off, I put the wiggly equal sign. For B, I get 21.217. For C, I'm getting 1.196. For D, I'm getting 32.758. For E, getting about 2.273. And then for F, I'm getting 18.813. Okay, so let's talk about exponential growth. And this has been all over the news lately because this does describe the way a virus spreads. So an exponential function looks like some constant times a base to a power, where the power is the variable. So you'll also see this written in different ways, like a b to the x. Well, as long as you have a constant and a base and the exponent on the base, then that's the variable. They really are the same, they're just using different letters. So in this setup where we have c a to the x, a has to be a positive real number. So we can only have positive numbers for bases, and the number can't be 1, and the capital C can't be a 0. Then the domain is the set of all real numbers, and A is called the growth factor. And because f of 0 is capital C is called the initial value. It's the amount you start with, whether it's a population or money or what have you. So why do we need the condition that A has to be positive? Well, we're taking the number A to different powers and looking at what the graph looks like. Well, if you had A was a negative number, then as you took it to different powers, you'd get a positive number, then a negative number, then a positive number. So your graph would be bouncing around from positive to negative numbers, and that's not exponential growth, because we know what that needs to look like. And then A can't be 1, because if A was 1, well, we just decided earlier that 1 to any power is 1. So this would be the graph y equals c, which is just a horizontal line That's not exponential growth either. And if c was 0, we'd have f of x equals 0. Again, not exponential growth. So that's why we have to have all those conditions. So I want you to make sure you're very clear on the difference between power functions and exponential functions. Look where all the pieces are. In the power function and the exponential function, we have a vertical, stretch, or compress factor for both. But in the power function, the x is the base, and n, some constant number in a given problem, is the exponent. So you're doing 2 to the power of 3, then 5 to the power of 3, then 12 to the power of 3, then negative 7 to the power of 3. That's a power function. The exponential function, you have a base and the variable is in the exponent. So the exponent is what's changing. So you'll have 2 to the 3 and 2 to the 4 and 2 to the negative 7 and 2 to the 12. So very different looking in practice, and the graphs look very different also. So everything we've already learned about transformations applies here. So let's do a quick refresh of those. So a right shift we subtract, a left shift we add before we do the function. Then up and down shifts happen by adding or subtracting after the function. Then vertical stretch or compress happens by multiplying after the function. And the stretch happens if a is bigger than 0. And the compress happens if a is between 0 and 1. So then horizontal stretching and compressing happens from multiplying before we do the function. And then this is counterintuitive to me, but the stretch happens if the multiplier is between 0 and 1, and the compress happens if the a is bigger than 1. Then reflection about the x-axis happens when you multiply by negative 1 after the function. And reflection about the y-axis happens if you multiply by negative 1 before the function. Okay, so for exponential functions, we'll show some examples. If you do 2 to the x plus 4, that's adding to the x before the function. If you do 2 to the x minus 5, that's adding or subtracting after the function happens. Then if we want to do the vertical stretch or compress, that has to happen after the function. So you could have 3 times 2 to the x, and that would do a vertical stretch. Then if you want to have a horizontal stretch or compress, you're going to have 2 to the 1/3 x, and you've multiplied the x by some multiple before you've done the exponential function. Then reflection about the x-axis would be like negative 3 to the x, and reflection about the y-axis would be 3 to the negative x. Okay, so for any exponential function, it turns out that if you do f of one number and then f of the number 1 larger, so if you do f of 4 in the denominator and f of 5 in the numerator, or f of 7.2 in the denominator and f of 8.2 in the numerator, you always get a, the base. And we'll see why in a moment. So another way of writing this is to say if you take a and multiply it by the value of your function now, you will get the value of the function at the x that's one higher. So what it's saying is to get from one value to the next, if you were a sequence, for instance, this would be like a geometric sequence where you're multiplying to get to the next guy. So if f of x is ca to the x, then we know that f of x plus 1 says everywhere you see an x, put an x plus 1. So then let's do this quotient where it says f of x plus 1 over f of x. And we can see that the letter c is going to cancel. And then when the exponents are arranged this way, I subtract them. And sure enough, I get a, no matter what a is. So if we're given some data and we're trying to decide how to model it, it can help to have a sense of how data grows. So let's look at linear and exponential models, because they're two really common ones. And we're going to look at some data and decide whether what we see is behaving in a linear way, an exponential way, or neither. Okay, so this first set of data, as x goes up by 1, do you see that the y value is going down by 3? So that's actually the slope, and the way to get the numbers to go down by 3 is you go negative 3x. So each time x changes by 1, y changes by negative 3. And then when x is 0, we can see that the y value is 2. So this is the equation that describes this data in table A. So this is linear. If you're adding or subtracting the same amount each time, a flat amount. So then let's look at B. And notice as x is going up by 1 and up by 1, we seem to be multiplying by something. So we're multiplying by 1/2. So that means 1/2 is the factor, and it's going to be to the power of x because it's exponential. And let's see, we know that we want something that looks like f of x equals ca to the x. And when x is 0, that's our capital C, so that's going to be 16. So we have f of x equals 16 times 1/2 to the x. So that's the model that describes this data. You're multiplying by something to get to each successive value. Then the last one, if I add 2, that's not working. If I multiply by 2, that's not working. So this is the neither. We'd have to come up with some other way of modeling this data. Okay, so let's go ahead and make a quick graph of y equals 2 to the x. So we'll make a little x and y table. When x is 0, y equals 2 to the 0, which is 1. So we know 0, 1 is a point on our graph. Then when x is 1, y equals 2 to the 1, or 2. So the point 1, 2 is a point on our graph. Then when x is 2, y equals 2 to the 2. So the point 2, 4 is a point on the graph. Then when x is 3, I get 8. And when x is 4, I'll get 16. And then let's do a negative value. When x is negative 1, y equals 2 to the negative 1, which is 1/2. And then negative 2, I'm going to get 1/4. So here is the shape of my exponential graph. and we'll talk more about it in the next video.